Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through the beginning section of Chapter 12, Three-Dimensional Coordinate Systems. So, yeah, that's what we're going to be discussing here, how to deal with something in the three-dimensional space. Up to this point, we've really only talked about that in relation to volumes when rotating some two-dimensional cross-section around some axis. That's the best we've been able to do in a three-dimensional space. However, when we are actually dealing with something that is defined in a three-dimensional coordinate system, we do need to make sure that we understand what that means. Typically, we call the three-dimensional space r cubed, or r to the third power, which means that you have one real number for each of the x, y, and z coordinate systems. So it tends to look like parentheses x, y, z for any specific point, where x, y, and z themselves are real numbers. A decent graphic here. This is coming from Wikipedia, so credit to that. This is showing how you would graph some point P based on its coordinates x, y, and z. Note that if I consider this point P and the origin, what I come up with is this sort of rectangular prism. Sometimes this is called a parallelepiped. But we see that this is made up of how much distance you go in the x direction, how much distance you go in the y direction, and then how much distance you go in the z direction. Or in any order of those. You could also go with z first, then x, and then y, and still end up at this point P. So we'll always, three pair of x, y, and z will always define a unique point in the coordinate system. Note that this is also tends to be how we graph the axes themselves. We tend to graph x here and y here, and then z going up this way. But it's always good to think about x being something that comes out of a two-dimensional plane. So if you look at x and y just as they are, this looks like what you're kind of used to, or z and y rather. This looks like a two-dimensional plane that you're used to, but then this one out here is coming out of the page, you could say. That is how we tend to consider the third coordinate, something coming out of the page that you're drawing on, which is why this one looks to be diagonal. Now, this is only really us drawing the first octant, we'd say, because this is true for positive x, positive y, and positive z. But you can imagine the negative versions of each going in the other directions. So negative y would go this way, negative z would go this way, and negative x would go this way. So negative z, negative x, and negative y. So now you can kind of see an eight quadrant system, where instead of a quadrants like quadrant 1, 2, 3, and 4 you may be used to on a two-dimensional plane. Here, since we have a three-dimensional plane, there's technically more sections coming out. There's actually 8 of them, hence why we will sometimes call them octants. Now, what we're first going to do in this three-dimensional plane is talk about different equations you can have. Talking about distance, midpoint, and also what it would look like just to graph just any given equation of a three-dimensional plane. So, first we're going to talk about how we would find the distance across from one point to another. So, say point A to point B, where A and B are defined like so. Now, A and B can show up really anywhere in the three-dimensional plane. If I define A here and B here, what I'm really trying to find is the distance from A to B. But remember, I have to think about A and B as three-dimensional systems. So, when I think about that, I have to think about, say, maybe A is sitting on the origin for ease of use. Then I think about B as a combination of a couple different vectors here. So maybe I'll put B here. It'll be probably a little easier to understand. So I'll have Z here, Y, and X coming this way. If I want to find the distance between these points, I need to consider how I would get from point A to point B. Well, to do so, I would travel some distance along the x direction. Maybe I'll do that in blue. And then I'd travel some distance in the y direction. And then I'd travel vertically some distance in the z direction. That would get me up to point B. Well, if I consider this as a triangle from point A to point B intersecting some point D here, I'll say, well, maybe C, I guess. Some point C. Well, then I should be able to find D by considering this as a right triangle, because this is intersecting the plane of X and Y. So this is a right triangle, it's just turned on the side, that's why the angle doesn't look like it's a right triangle. But it's really just going to C going vertically up, so this should be perpendicular. That means I should be able to define this in a two-dimensional respect, thinking about the distance from A to B, whatever that distance is, as AC squared plus CB squared. Now, A and C we're not exactly sure about, but C and B, this is just the distance in Y, or in the distance in Z. So this is the same as just Z squared. So far we have AB, which is the distance we want, is equal to AC squared plus Z squared. Because C and B is simply traveling in the one direction Z. There's no other change in X or Y. But A and C is a little bit more complicated. Both X and Y change as you travel along the line AC. That line being right here. But if I look at that blue triangle that I have on the side, I notice that this also is a right triangle, with AC being defined as the hypotenuse. So I see that AC squared as the hypotenuse would be defined as, maybe if I define this point as D, I'd say that that's AD squared plus DC squared. However, both AD and DC are just changes in one variable. AD is just the change in X, so that's X squared, and DC is the change in Y squared. So since I know that AC is the same as X squared plus Y squared, I should then be able to say then that D squared is X squared plus Y squared, that's what AC squared is, plus Z squared. That generally is my distance formula. Now to be more accurate, we'd actually consider these the change in X, Y, and Z. So you'd say D squared is, not A, you'd say it's delta X, the change in X, plus the change in Y, plus the change in Z. Each of these changes, the change in X you can define as just the difference between X coordinates. So in this case for A and B, the X coordinates would be X2 minus X1, Y would be Y2 minus Y1, and Z would be Z2 minus Z1. That leads us to our general definition for the distance in 3 dimensions as the square root, if you square root to both sides, of the change in X squared, the change in Y squared, and the change in Z squared. Note that this looks a lot like the distance formula from 2 dimensions. It's just adding that extra bit right here. It's just adding an additional coordinate to it. You'll see this as a common theme between 2-dimension and 3-dimensional space. The formulas will look very, very similar, just a small change. And that's usually just adding a component that would be the 3rd dimension. So it transfers over rather nicely. Likewise, to go along with that line of thinking, if you consider the equation of a circle in the 2-dimensional space, we know that as x minus a squared plus y minus b squared equals r squared, where you're centered at AB with radius r. And if you're doing it in a 3-dimensional space, that would be a sphere, and a sphere is defined as the same way, just adding an extra component of z. So we have the equation of this sphere defined as x minus a squared plus y minus b squared plus z minus c squared equals r squared, where now you're centered at a 3-coordinate point ABC. This equation is sometimes written out if you FOIL this. If you FOIL x minus a squared and y minus b squared and z minus c squared, you end up with x squared, y squared, and z squared, some amounts of x, some amounts of y, some amounts of z, and then a constant. That constant coming from all of three of these pieces. There'll be a constant that comes out of x minus a squared, a constant that comes out of y minus b squared, and a constant that comes out of z minus c squared. That combined with the constant of r squared, just we can call that some variable j. The reason I bring this up is because we should be able to take an equation that looks like this and rewrite it into the more standard form for a sphere and talk about where the center and radius is. And that's what I'm going to do in the first example here. So in this question, we're going to find the center and radius of the sphere defined by x squared plus y squared plus z squared. That should actually be a minus 10x minus 8y plus 12z plus 68 equals 0. All right, now in order to make this into a sphere, what we're going to do is combine all the terms that are alike. So I'm going to combine x squared with that minus 10x. I'm going to leave some space. I'm also going to combine the y's, so y squared minus 8y, and leave some space, and do the same thing for z. Plus 12z, leave some space, and I'll just throw that minus 68 to the other side. Now the reason I leave some space is because this should look pretty familiar now. We should know how to deal with each of these and try to come up with something plus something squared. I'm going to need to complete the square. Reminder that the easiest way to complete the square is to take this value, have it, and then square that. So I'm going to take negative 10 divided by 2, and I'm going to square that. And that number goes here. So negative 10 divided by 2 is 5, or negative 5 squared is positive 25. I'll write those in blue. I'm going to take negative 8, have that, and square it. And I'm going to put that here. That'll make 4 squared, which is plus 16. And then I'm going to take 12, have that, and square it. So that's going to be 36 right there. Now remember, if we complete the square, we can't just add and subtract these numbers willy-nilly. We do need to compensate for that by putting on the other side. So if I added 25 onto the left side of this equation here, then I likewise need to add 25 to the right side, and also 16, and also 36. What that will leave me with is x squared minus 10x plus 25, which is going to be x minus 5 squared. Y squared minus 8y plus 16 is going to be y minus 4 squared. If you have trouble defoiling these, you should note that this minus 5, this negative 4, is also this number, just without the square. And then z, we get z plus 6 squared. On the other side, we find if we do negative 68 plus 25 plus 16 plus 36, should get a total sum of 9. And so now we have our equation of the sphere, and we should be able to define the center and the radius. In this case, we are centered at the coordinate 5 for x, 4 for y, and negative 6 for z, with a radius of 3. Okay, so just a little bit of algebra manipulation there. You can also extend these concepts into the midpoint formula. The midpoint formula will be just like the normal midpoint formula. The only thing is that you add an additional piece here. You will do this on your homework, and I have a hint here saying that I suggest utilizing the distance formula, which we had on the first page, and set up an equation for the distance from one endpoint to the other equal to the or half of the distance from one endpoint to the other. So say from A to B, find that distance, set up that formula, and then set that equal to half, or set that to be half equal to the distance of one endpoint to the midpoint. So if you're trying to find from A to B, and you're trying to find the midpoint here, then you should be able to find the distance AB, and that's going to be half the distance from A to, say, M, or B to M, whichever one you'd want. Set up both of these and solve, and you should be able to come up with midpoint values. Okay, but I'll leave that to you. Now, in the three-dimensional space, if you do have an equation that involves just the singular values of x, y, and z, so to an exponent of 1 or a degree of 1, then what you're actually going to define is a plane. For example, if you have y equals 3, what that means on a quick plane here, y equals 3, we would usually write y over here, so 1, 2, 3. Y equals 3 means this line, but doesn't also only just mean that line, it also means all x and z values that could be true for y. Right now I just have all those z values that are true, but x could also be true, so what you actually define is a plane that goes through that place. So what this looks like is basically a plane like so, like a piece of paper. If you have something a little bit more complicated, for example, we have x plus z equals 2, then the best way to think about that is to consider where you would intersect the x and z axis. X is this axis, we'd intersect at 2, and we'd also intersect z at 2. You could consider setting x and y equal to 0 and then solving for z, setting z and y equal to 0, solving for x. And we know that this makes this line here. However, again, this could be true for any y values. So this actually is creating a plane like so. And this plane continues on in infinity in all directions. So you're creating a slanted sheet of paper. This is how I'm going to define most of these equations. I recommend trying to solve for each of the variables, placing those points down, and then connecting those as a plane. For example, here we have 2x plus 3y equals z. Alright, well, let's say x equals 0 and z equals 0. Then what we have is 2 times 0 plus 3y equals 6, or just 3y equals 6, and therefore y equals 2. So now I have a point. I have a point x, or I have a point of x being 0, y being 2, z being 0. Just like if you were to plug in and find points on a line by plugging in any given numbers. I could do the same thing for, say, I set y equal to 0 and z equal to 0. Note that z actually isn't even relevant here. If I plug in y and z as 0, I get 2x plus 3 times 0 equals 6, or 2x equals 6, therefore x equals 3. So I now have a coordinate 3, 0, 0. If I graph this, x, y, and z, what I will do is put both these points down. 3, 0, 0 would be 1, 2, 3, be right there. 0, 2, 0 would be 2 in the y direction, which would be right there. And then I have a line between them. That line is defining a plane that is true for all z values. So up this direction, down this direction, down this direction, and technically out as well. This is what I'm creating, a sheet of paper, or a plane sheet like this that goes through this value. That's part of it. So that'd be a graph of 2x plus 3y equals z on the three-dimensional plane. We can also do that if we have all three values, 3x plus 4y plus 2z equals 12. Again, just set two of them equal to 0 at a time and solve for the other. So if I have x equal, let's solve for x first. So I'll set y equal to 0, z equal to 0. Solve for x, we get 3x equals 12, or x equals 4. So we get 4, 0, 0. If I set x and z equal to 0, then I get 4y equals 12 and y equals 3. So I have 0, 3, 0. And lastly, if I have x and y equal to 0, I have 2z equal to 12 or z equal to 6. So 0, 0, 6. Graphing that, x, y, and z. If I graph this x coordinate, that's going to be 1, 2, 3, 4, right there. If I graph the y coordinate, that'll be 1, 2, 3, right there. And then if I do another color, say green, for the z coordinate, I have 1, 2, 3, 4, 5, 6, right up there. And then what I do, I connect them, just like I did before. But now what I do, I'm creating this triangle plane. Anything within this triangle or on this triangle itself would be a solution set for 3x plus 4y plus 2z equals 12. It's not just these three numbers or the numbers on this these lines. It could also be the numbers in this plane. But remember that this plane can also continue in all directions. So you can think about this like a corner of a room or something, and you have something slanted up against it. Then if that plane, that the thing that you have slanted up against it, continues on in all directions through the wall, that would be what this plane looks like. So it continues in all these directions. It just happens to intersect the x, y, and z axes at these points. So those are a couple examples of graphing some things in three-dimensional plane, and just a quick overview of some concepts in there. If you have any questions, feel free to put those in the comments below, or you can ask your instructor directly. With that said, I hope you have a nice day.